Hello everyone, I'm Dr. Priya Kansal and today I'm going to present my work co-authored with Sabri Nathan on Instagram filter removal titled as Internet Recurrent Residual Network for Instagram Filter Removal. This allow their users to archive, organize and share their collection of pictures. Beside these core functionalities, they also offer many other features such as editing, tagging, searching by content, creating albums, etc. One popular feature is the option to apply photographic filters to change the mood of the picture in a completely automatic way to make images aesthetically pleasing. These filters apply certain complex transformations to do this task. For example, there is a shift in color distribution, brightness, in contrast of the images. Also, they can introduce the smoothness, the color curves, and the vignettes to the images. However, some recent studies show that these corruptions and permutations degrade the performance of the convolutional neural networks on different downstream vision tasks. For example, classification and segmentation. This, moreover, this image corruption reduces the trustworthiness of many image forensic tasks such as sensor pattern, noise-based provenance analysis. Therefore, it is crucial to mitigate the impact of filters before any visual understanding task, specifically in which social media images are the main input. This task of understanding the filters in social media images has been addressed in several ways. Few studies have classified the types of filters applied to the images. Some studies attempted to learn the representation of these filters. However, a very few attempts are made for the end-to-end retrieval of the original images. In some studies, the problem of filter removal has been considered as the problem of style reversal. We have considered this problem of filter removal similar to the problem of image restoration, especially similar to image denoising, wherein the most of this state-of-art networks are trained to learn the feature representation of noise, which in this case is style or the Instagram filter, and then the original image is retrieved as a residual of the input image and the learned feature representation. So this is the proposed architecture. To retrieve the original image from the Instagram filter styled image, we propose a simple unit with recurrent residual blocks in the encoder and decoder. The proposed network took advantage of three state-of-art deep learning methods in one architecture. One is residual block, second is recurrent convolution layer, and third is unit. The main property of unit is the skip connections. The skip connections between encoder and decoder at different stages help the model to learn both local and global information without losing its spatial and channel level pixel information. Similarly, a simple residual block consists of addition of residual features to the inputs to take care of two important attributes. First is vanishing gradients and second is loss of information in a higher layer. Further, the main advantage of using recurrent convolution layer is that even if the input is static, the units of each layer evolves over discrete time steps so that activity of each unit is modulated by the activities of its neighboring units. Because of this characteristic, the network learns contextual information more efficiently and effectively. Moreover, the learning process of the network is benefited by the arbitrary number of paths of the unfolded recurrent convolutional layer uh, through time with a fixed number of parameters. We have conducted an extensive evaluation and compared it with the existing state of art to prove the efficiency of the proposed network, which I will be showing in the next slides. As far as dataset is concerned for this paper, we use the IFFI dataset, which consists of total of 15 filters and one original image. Hence, for every ID, there are 16 copies given in the data, including one original image. So there are total of 500 IDs given for training with their ground truth. For training purpose, the 500 IDs are split into training and validation. Hence, the first 400 IDs are used for training and rest 100 IDs are used for validation data. Uh, so this is the loss function. Since the proposed model aims to learn the residual mapping of filters injected into the original image, the combination of average mean square error and the Charbonnier loss is used as a loss function. So here are the training details. For as a pre-processing step, we normalize the images between 0 to 1. We used EDM optimizer and we initialize the learning rate with 0.001, which is reduced by 10% with the patients of 15 epochs. We use the evaluation metrics as PSNR and SSIM index. So here is the result. Here are the quantitative results. So as I have mentioned that we performed a extensive ablation study. We basically compared the results based on two approaches. One is denoising architecture and other is generative architecture. First of all, from this table, it is clear that denoising architecture in all the type of denoising architectures are performing better than the generative architectures, state of art generative architectures. When it comes to our proposed network, it is very evident from this table that our proposed network has uh, outperformed all existing state-of-art generative architectures and as well as image denoising methods as well as the existing state-of-art methods for IFFI dataset. So this is the qualitative comparison. This is the comparison of the results of the proposed network as well as the existing state-of-art network, denoising network, for example, MIRNet and NAFnet. And we also compared our result with simple residual UNet and uh, plain U network, and it is clearly evident from the results that in terms of color, contrast, smoothness, the proposed net is performing better than the other. This is the result comparison with the generative architectures like Pix2Pix, Grid plus GC Angular GAN, Cycle GAN. So these results are taken from the base paper of IFFI dataset, and this clearly shows that proposed network is much better than the results generated by state-of-art generative models in terms of unwanted color. We can see the unwanted colors, some reduced brightness in the images which are generated by the generative architectures when compared to proposed network. So this slide shows the filter representation learned by the different architectures that has been used in ablation study. For this figure, we can see From this figure, we can see that simple UNet and MIRNet are not able to learn any representation for the filter. However, the proposed network and NEFNet seems to learn similar representation, but if we go deeper, we would be able to realize that NAPNet is actually learning the features related to the contrast injected in the image. Yes, so here comes the conclusion. We have used residual learning and recurrent learning to create an end-to-end efficient network for photographic filter removal. This can be the most basic architecture that can be used for image retrieval task. In this case, if an Instagram filter removal task without any fancy losses, complex losses, and complex optimizers or complex backbone blocks, and everything. As far as future work is concerned, so we would like to create a lightweight network for the filter removal, as well as we would like to add the filter classification as an auxiliary task. This is all about the presentation. Thank you for patience hearing. We would like to welcome all questions and suggestions. Please write to this mail ID. Thank you so much.